So let us continue our discussion on several variable calculus, and in this lecture, so this is I guess lecture 5, and in this lecture we are gonna discuss about the chain rule. Okay, the chain rule. Okay, so let us first write out the statement and then we will be proving it up. So suppose E is a set in Rn, F is a map from E to Rm, and F is differentiable at some x naught in E. Let me choose E to be open. Okay, let me just choose E to be open because we have been defining the derivatives in the interior points. Be open. Yeah, so whenever we choose E to be open, so any point I talk about differentiability, that is automatically an interior point. So if it's differentiable at x naught in E, and let G be a map, let's say G is a map from some F to Rk, and G is, okay, let me not use F, let me simply write it like this, and let G be a map from an open set containing f of E. So the point f evaluated at x naught is then an interior point of this open set, so containing f of E into some space Rk. Fine, and G is differentiable at f of x naught. Fine, then the map f from E to Rk by, so what we are basically doing is that we are composing up f and G. So yeah, so f was a map from E to Rm and G is a map from Fe to Rk. Yeah, so this map should be G composed with f. Okay, so then this is differentiable. Then this is differentiable at x naught, and the derivative is given as f prime at x naught is G prime of fx naught composed with f prime at x naught. Why am I using the word composed with? Because we know that by the definition of derivative these are linear transformations, right? Fine. Okay, so let's see the proof of it. So what it basically tells is that if I can approximate a function f at some point x naught, and I can approximate G at the point f x naught, then I can approximate their composition using a linear transformation which is given by the formula which is just provided, right? To prove this, let me first give out an important observation which I should have given in the previous lectures, which I have missed. See the way we have evaluated the derivatives. Okay, so it was limit x tends to x naught, x is not exactly equal to x naught, and it was given as the norm of f of x minus f of x naught minus the derivative at x naught at x minus x naught divided by norm of x minus x naught is equal to 0. So this was our basic definition of derivative, right? We slightly manipulate out this derivative in this way, so which is equivalent to saying limit h tends to 0. So what we are specifically doing is that we are choosing the vector x minus x naught to be h. Okay, so limit h tends to 0, norm of, then x becomes x naught plus h, right, minus f of x naught minus f prime at x naught times h, or rather at h divided by the norm of h. So this is equals to 0. So this approximation, this can be equivalently written as that f of x naught plus h minus f at x naught this is f prime at x naught h plus some function rh, which we call the remainder function. So this can be thought of as the remainder function, or this can be also thought of as the as some error term. Okay. Now what is the property which RH follows, where if I just slightly manipulate this statement into the statement of derivative, where limit h tends to 0, the norm of RH divided by the norm of h, this is 0. Fine, right? We have this in hand. Okay, fine. So this gives an equivalent way of writing the derivative in terms of a remainder term, and this is often sort of used as a Taylor expansion as well, but whatever, that's not required at this point. So we will be using this in the proof. So let's go for a proof. So for simplicity, we choose y naught to be the point f at x naught, and we choose let's say we denote a as the linear operator f prime x naught. We choose b to be the linear operator g prime y naught. These linear operators help us approximate the function f and g, because we are given that f is differentiable at x naught and g is differentiable at y naught. Fine. Now define the function uh to be f at x naught plus h minus f at x naught minus ah. Okay. Now this seems to be in compliance with the definition of derivative. We will see why is it so. Fine, this is there, and let vh, or rather sorry, let vk be the g at y naught plus k minus g at y naught minus bk. Okay, achha, wait a minute. Yeah, okay, yeah. So we have this, and this is defined for all h and k, or rather I should specifically mention where they belong. So h should belong in Rn, right, because this linear operator will be defined on Rn, and k is then in Rm. Fine, for which these vectors are defined, for which f at x naught plus h and g at y naught plus k are defined, right? Then immediately, since f is differentiable at x naught, what do I have? So if I take norm on both sides, then there will be some remainder term due to this derivative, right? See, this is approximated by a function. If I just quickly go back, then this is approximated by some remainder term RH, and we can choose this. Yeah, so I have this remainder term RH, which goes to 0 as h goes to 0, right? Yeah. So yeah, now what we can do is here, yeah. So since f is differentiable at x naught, then if I take norm on both sides and if I multiply by h throughout, if I have a so I have here, I can represent this remainder term as some other remainder term epsilon h times the norm of h, right? I can do that, and that will still go to 0. Fine. So then I should say that then there exists epsilon h, a function which depends on h, such that the norm of uh, this is equals to epsilon h times the norm of h, where this epsilon h goes to 0, where, or rather I should have included here epsilon h which goes to 0 as h goes to 0, such that this happens. And similarly I have norm of vk to be some eta k times norm of k, such that eta k goes to 0, as k goes to 0, right? Now choose the vector. Now choose k to be this vector fx naught plus h minus f of x naught. Fine. For some given h, for some given h. Okay. Then observe, then what is the norm of k? Then the norm of k is basically norm of this, but norm of fx naught plus h minus fx naught, this can be written as norm of uh, plus ah, right? So this is equals to norm of a at h plus u at h. Now this is by triangle inequality less than equals to norm of ah plus norm of u uh, right? But we know that in case of whenever we have a linear operator, then by Cauchy-Schwarz inequality, or rather I don't think it's a Cauchy-Schwarz inequality, this follows from the continuity or the boundedness of a linear operator over finite dimensional spaces, that this is less than equals to norm of a times norm of h. So this is that's the operator norm, plus, and we have just proved that the norm of this is equals to epsilon h times norm of h. So this is equals to norm of a plus epsilon h, this times norm of h. Fine. Yeah, this will something good to go. And now we evaluate f of x naught plus h minus f at x naught. So and minus b a h. So b composed with a applied to h, right? Now this by definition is basically equals to, so f is g of f, and so g of f is, so g of f at x naught plus h is g applied to f of x naught plus h, that's just g of y naught plus k minus g at y naught. So how does this follow? So let me just add an extra step. So this is equals to g of f of x naught plus h, fine, minus g of f of x naught minus b a h, right? But how had we chosen f of x naught plus h? There was a representation in terms of k, right? F of x naught plus h minus f of x naught. This was something which we have chosen. And what was our y naught? Y naught was simply f x naught. So this becomes, therefore this becomes g of y naught plus k minus this becomes g of y naught minus b a h, right? But then g at y naught plus k minus g at y naught, then this can be further written as vk plus bk, b applied to k minus bah. And so if I choose, if I take out the b outside, I get it to be b applied to k minus ah plus vk. But then k minus ah, this again by definition, so k is just f of x naught plus h minus f of x naught minus ah, that was just u at h, right? So this is b applied to u at h plus vk, fine. Now just divide by h and take the norm. So this implies that the norm of fx naught plus h minus fx naught minus bah divided by the norm of h. So what will this give us? So this is so this will be this norm of b applied to uh plus vk, this divided by norm of h. But then we can again use the triangle inequality and bring out the operator norm of b. I will get by norm of h, but by norm of h will be just epsilon h, right? So this should be less than equals to, or rather if I add an extra step, so this should be less than equals to norm of b times norm of right? And what should I have here? So I had plus norm of vk, which was simply eta k times norm of k divided by norm of h, right? Now norm of by norm of h was simply epsilon h plus, and this can be manipulated to form norm of A plus epsilon h times eta k, right? How does this come? This immediately comes from how we had represented norm of k. We had seen that norm of k was simply less than or equals to, yeah, so this should be less than or equals to, right? Yeah, so since we had proved that norm of k is less than or equals to norm of A applied to h plus plus epsilon h, this complete thing, I'm confusing it itself. Yeah, so this was norm of A plus epsilon applied to h times the norm of h. Yeah, correct. Yeah, now it's done, right? So we have this, but then as h tends to 0, the RHS, if you observe, then epsilon h tends to 0. This is something which we already have. And what more we have? Also k tends to 0 as h tends to 0. Why is it so? It follows from the fact that norm of k was less than or equals to norm of A plus epsilon h times the norm of h, right? So also k tends to 0, and hence eta k tends to 0, right? And thus this implies that the limit h tends to 0, norm of f of x naught plus h minus f of x naught minus BAH divided by the norm of h, this becomes 0, which implies that f is differentiable directly from definition now, that f is differentiable at x naught with f prime at x naught to be BA, right? And what was B? So B was G prime at fx naught, and what was A? A was f prime at x naught. Fine. So this immediately gives us the chain rule. Yeah, the proof was not difficult. It required at some points the notions of linear operators. That's it. That was the exact thing which we required, and the other things were just, simple manipulations, simple algebraic manipulations. A simple corollary to it, wait a minute, yeah. A simple corollary to it would be what should be the Jacobian, okay? And if you recall, then the Jacobian of the G composed with f at x naught, then this should be exactly equal to the Jacobian at G at fx naught multiplied, so the matrix multiplication, the Jacobian of f at x naught. Fine. Yeah, you can analyze this immediately from the way the derivative forms, and if you are not convinced by that, you can simply find out what the elements here looks like, and you will see that it exactly imitates this form, right? And you will have a good result. But rather it's quite immediate from the chain rule. It's immediate from the chain rule, right? Fine. Yeah. So in fact, this matrix statement actually gives us a good way to find the derivatives of compositions of differentiable functions. Yeah, so that's where basically whenever you are calculating derivatives, it's better, we have seen in the previous lecture that it's quite easy when you consider the matrix form, and in the same way whenever you are calculating the derivatives of compositions of two differentiable functions at some point, it's better to calculate that using the derivative form, using the matrix form, right? Yeah, fine. So let this lecture be up till this much. In the next lecture we will be coming up with something more. I guess we will be start discussing about the double derivatives. Okay, yeah, so meet you guys in the next lecture.